Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will be talking about the Lagrange equations and how they can help us get the equations of motion in an even simpler manner. So we know the principle of virtual work already and even the principle of the generalized coordinates. But the problem with this principle is that we still require a lot of massaging of our equations to get to the simple equation of motion. Sometimes we have to do way too much work for a little system where the equation of motion should be very obvious. So this is where we start with the energy part of the analytical dynamics. So the energy itself is basically the ability to do work. So energy and work are very, very similar in our context. So now what we are going to do is use the energy that is inside our system to get the equations of motion. So like we know from high school, the kinetic energy is a half times the mass times velocity squared. We go by a half times mass times displacement derived with time squared. And because we have multiple bodies and multiple directions, we have to sum up over all directions and bodies. So we have mass K and the displacement of body K in direction I. And don't forget the square. What we now see is if we derive our kinetic energy, like we had it here, first with derive the kinetic energy with u dot, we get, so let me write that out, we have 1.5 times m times u dot. We derive it once with our u dot, we get, don't forget the squared, like I said, we have m times u dot. And now we have to do a time derivative, so you go dt, and we get m times u double dot. So that's how we get from the kinetic energy to our inertia forces. They're not forces exactly, but we treat them like inertia forces. So now we know how we can substitute our inertia forces with the help of our kinetic energy. So that's what the principle of virtual work looks like, where we had m times u double dot right here, but we replaced it with a time derivative and a partial derivative from our kinetic energy. Now we have to do a little bit more work because we don't like that we have to do a partial derivative with respect to our u dots. So let me get a new color. If we have this term and we do a expansion, we apply this time derivative to the first term and to the second term, and then we have a sum. So let's make this yellow and make this one, let's say blue, for example. Now we have two terms that we expanded. And if we look closely, we see that this term is exactly the yellow term. So let's make it yellow. This right here times this one is exactly the yellow term. So we can replace the yellow term with the orange and the blue one. So the orange term goes here and the blue one is here. We have to do a minus right there because this minus that equals the yellow term. So now we have an even bigger problem, or not problem, but something that looks even more complicated, but we will work on that and make it very simple. We still have derivatives with respect to our u dots, and this is something that we need to get rid of. If we look at the total derivative of our positions, we know that we have to derive partially first with time, and then we have again a sum of all partial derivatives with respect to our q's. And if we derive this expression partially with our q dots, like we did right here, this is gone because this is not dependent on q dots. This q dot is gone, and we are only left with this expression. And we call this as something called cancel the dot rule. You can't always cancel the dot in every mathematical expression that you have, but in this specific case, we can treat them both as the same. So if we have two dots, we can remove them. And if we don't have two dots in a partial derivative, in this case, we can add them. So let's look at the term that we had before. We apply the cancel the dot rule right here. So we get a du dot dqs. And this time derivative, we apply it to the top part. So here it doesn't matter, the order of differentiation doesn't matter, so we can apply it first to the top part and then derive with our q's. If we have this, we see that we have a du dot right there and a du dot right there, so this cancels out. And we have a partial derivative here and a partial derivative there, so we get rid of this. And what we are left with is this simple expression. We still have the bodies and the directions, but we can get just rid of them because the kinetic energy already sums up over all bodies and all directions. So this can also be gone. The only thing we have to consider is our generalized coordinates, so our degrees of freedom, and they go, of course, from 1 to n. So we are left with this easy expression, or expressions, because we have, of course, multiple of those. But we're still not done yet. We only considered the not the forces, but the kinetic energy in the system. But we did not consider gravity or something like dampeners or friction or something like that. That's why we then have to work with our Q's. So if a force can be derived from a potential, we call it conservative. So V in our case is the potential of our system. For example, if I move a mass, the mass has more potential. In gravity, if we derive it with our position, if we derive the potential with respect to our position, we get the force of gravity that is acting on the system. So our x's are forces derived from our x's are forces derived from a potential, and thus they are conservative because a potential will be transformed into kinetic energy. So we can write it like this. So now we have the forces, the conservative forces are our potential energy derived with our q's with u times du dqs. The u's cancel each other out, and we are left with our potential energy partially derived with our q's. Exactly the thing that we want. So in our final equation, we only have the part that we had right there before. Here we have our potential energy, and now we only have our non-conservative forces that are acting on the system, like dampeners or like friction. Springs and gravity are part of the potential, and they are included in our V. So we have n equations, and this simple structure will get us the equations of motion right away. To get it, to understand it, I have a small example. So we have again our pendulum, and we get the kinetic energy first. So we have 1.5 times 1/2 times m times our positions derived with time squared, and this is 1/2 times m times L theta dot squared, because length is not changing, this stays constant, but the angle is changing with theta dot, and don't forget the squared. And then we have the potential energy, that is mgl times 1 minus cosine theta. The thing we have to do now is just to derive it and then to sum up, and then we get our equations of motion. It's just as simple as that. The derivation itself is a little bit complicated, but you don't have to do that for the exam. You just have to see it once and understand that we're coming from the kinetic energy, because energy is the ability to do work, and we need work like we needed work for the principle of virtual work, and now we put the kinetic energy into our principle of virtual work. did a lot of massaging again, but we only have to do it once, and got these simple equations. So back to the example, we have our kinetic energy and we have our potential. We derive our potential first with our Q's. So with our Q's, exactly. Q dots. Don't forget that we derive by Q dots. And our Q in this case, Q is theta. So our Q dot is theta dot. And we derive it once, so we're only left with ml theta. We derive it with time, and we're left with ml squared theta double dot. If we derive our kinetic energy just with our Q's, we see that we get 0 because our potential energy is not dependent on our Q's. If we derive the potential energy with our Q's, like we need to, we get ml times sine theta. And now we just have to sum everything up, and we get our known equation for our pendulum. We get rid of the m and the l, get rid of it, and we have our simple expression of our equation of motion. So to summarize again, let me reiterate. We get the kinetic energy and we get the potential energy. We know that we can substitute the kinetic energy and the potential energy in our principle of virtual work and basically get rid of the sums like this. And we are left with a simple equation where we know that the potential energy is something that will be conserved. We are only left with the non-conservative forces. We will talk about them in an example. So now we only have to do is derive the potential energy and the kinetic energy with our Q's and Q dots and derive it once with time, and we get the equation of motion. This system is very, very nice because it will help us we can just look at a system and see how the particles are moving. So get the positions of them, derive it once with time, and then then we already have the speeds. And if we have the speeds, we can get the kinetic energy. So we don't have to do a lot of transformations, do a lot of matrix multiplications. We can get the equations just with the help of this equation. I hope I could give you a small introduction into the topic of the Lagrange equations. If you have any questions, feel free to ask them in the comments down below, and I will do my best to answer them as quickly as possible. Thank you very much for your attention, and see you next time.